Okay, here's an ALEKS thermochemistry problem for us to do. And it states this 55.2 gram sample of glass is put into a calorimeter over here that contains 200 grams of water. The sample starts off at 94.5 degrees C and the temperature of the water starts off at 18 degrees C. So the water is there and the glass is actually much hotter. When the temperature of the water stops changing, it is heated up to 21.4 degrees C. It wants us to calculate the specific heat capacity. Okay, I think we can do that. Let's just remember a couple of things though. That the change in energy of the water is going to equal the opposite of the change in energy, in this case of the glass. Okay, so as energy moves from the glass into the water, then they're going to have opposite signs. Okay, so that's conservation of energy, energy moving from surroundings into the system or vice versa. Okay, so we also know that delta E equals specific heat capacity times mass times a change in temperature. Okay, since these things are at equilibrium, we can say that specific heat capacity of the glass times the mass of the glass times a change in temperature of the glass equals negative, the opposite of the specific heat capacity of the water times the mass of the water times delta T of the water. Okay, so we are trying to find what is the specific heat capacity of the glass. We have the mass of the glass. We can calculate the change in temperature of the glass. We can look up the specific heat capacity of the water, which we're going to call 4.18 joules per gram per degree C, times the mass of the water, which we have at 200, times the change in temperature of the water, which we can calculate. So we are giving all of this right here. Okay, so we can actually rearrange this equation to say the specific heat capacity of the glass is going to equal minus the specific heat capacity of water times the mass of the water times change in temperature of the water divided by the mass of the glass times delta T of the glass. Okay, I just rearranged this equation up here. It's a big long thing. I just rearranged it right here. Let's just quickly calculate our delta T's here. So delta T is always going to be T final minus T initial. Okay, so for the glass, the final for both of these, since it's at equilibrium, is going to be the same. So 21.4 is when everything changes. So if we have 21.4, let's do the glass. The glass started out at 94.5. Subtracting T final from T initial. When I do that for the glass, I get negative 73.1. Okay, that's the delta T for the glass, which we'll plug in right there. And now for the water, again, the final is the same since it's at equilibrium, 21.4. It started off at 18. And so if I do that math right there, then I get 3.4. Okay, so this has its 18.0. Let me get my sig figs right there. So this right here has 2 sig figs, and as I look throughout all my values given right here, then that is going to be guiding me, those 2 sig figs, in terms of sig fig. So now we can just plug everything in. That is, the specific heat capacity of the glass is going to be equal to specific heat capacity of the water. I'm just going to rewrite this equation over here, which is 4.18. That's going to be joules per gram per degree C times the mass of the water is my next, and that is given to me as 200.0 grams times delta T of the water, which I calculated over here to be 3.4 degrees C. Again, I'm just plugging in to this equation right here the actual values, divided by the mass of the glass, which is 55.2, times the change in temperature, which in this case is a minus 73.1. And just looking at one small mistake, I forgot to bring that negative over. So that'll be a negative right there. So when I do that math, I'm going to have a negative divided by a negative, which is a positive. Then I find that the specific heat capacity of this glass, I'm just going to call it G, equals 0.7044 on my calculator. Remember, it has 2 sig figs. So the specific heat capacity of glass, the answer to this problem, is going to be 0.70 joules per gram per degree C. Okay. So again, some of the key concepts here, just remember that because we have a system and surroundings here, and we're limiting the surroundings, at least in this case, to inside of here, then I can say that the change in water is going to be equal opposite the change in the glass. That the flow of energy is going, in this case, from the glass into the water. And using that, I can then set these two values equal to each other right here, and then I can just plug things in. So these are doable problems just after understanding what's going on.